So it's a pleasure to introduce Darrick Chang as our two-farm seminar speaker for today. Darrick is a professor at ICFO, which is the Institute for Atomic Sciences in Barcelona, and he's also affiliated with the Catalan Institution for Research and Advanced Studies. He actually did his bachelor's degree here at Stanford in physics, and then moved on to Harvard for his PhD, where he graduated in 2008 and moved on to a prize postdoctoral fellowship at Caltech. Darrick has been at ICFO since 2011, and there he leads the theoretical quantum nanophotonics group and has done really beautiful work that has been, I would say, very inspiring also for pushing experiments in new directions, such as building sub-wavelength atom arrays that manipulate light. And he's received a number of prestigious awards and grants for his work, including the ERC Starting Grant and more recently the ERC Consolidator Grant. And we're very happy to have him here today. His latest work, and one more for that.
So thanks a lot. Thanks a lot for the invitation. It's really a pleasure to be here. Let me just start off by acknowledging my group, especially Charlie, Whiting, and Mark, who did most of the work that I'll be talking about today. So I think this is probably a diverse audience. So I'd like to maybe start with a little bit extended motivation of we'll try and more close exactly what question it is that we're interested in these days. So probably I work in the field of quantum optics or quantum atom light interfaces. I think everyone has heard of these systems, at least in some form. And some of the applications that people are interested in, they don't really function. So these systems can be used to create quantum memories for photons, maybe photon gates for quantum computing, quantum metrology, sensing, spin sweeping, and maybe even kind of some many-body physics with atoms and light. So all these applications are being done in labs to some extent. But the kind of recurring theme, I would say that for a lot of the experiments, they work, but probably not as well as we wanted to. And there's kind of underlying challenge, if you want, that underlies all these. What makes these experiments difficult is that if you think about the building blocks of atom-light interfaces, single atoms, single photons. Fundamentally, it's just these things are these objects don't want to interact efficiently with one another. So to find efficiency, you can think about it if you want as a problem of collection efficiency. So imagine I have a kind of single atom, I bring it up in space, say it's going to emit a photon. That's going to emit in a kind of 4 pi dipole radiation pattern. And the problem is that it's hard to collect 4 pi light. So what you can easily collect is from a kind of nice Gaussian mode. So for example, you can try to focus a beam down to a beam waist W or area square. And then the problem is that that Gaussian beam doesn't cover 4 pi solid angle. It covers a solid angle that's given by lambda squared over W squared. So that essentially kind of collects that essentially establishes your collection efficiency. You can also think about the notion of efficiency by just kind of taking that movie and playing it in time reverse. So you can also define efficiency as I send in a photon. I try to excite a single atom. So I shine in a photon on resonance. And you can ask what's the probability that a photon kind of excites the atom, and the atom rescatters that light into other directions. And essentially by time reverse symmetry, that interaction probability is the same as what I showed earlier, lambda squared over the beam area. And so if you literally try to build this experiment where you take a single atom in free space, couple light resonance to it, the state-of-the-art kind of interaction efficiencies you get are on the order of a few percent. But what we really want is 100%. If we could get 100%, then essentially any application that we want to carry out in principle becomes perfect. So that's a kind of well-known challenge. And there's some well-known kind of fixes or common approaches that people use. So one is called cavity QED, where instead of a photon, having this photon pass through an atom a single time, you try to make the photon bounce back and forth by some number of bounces, and then the interaction gets enhanced by the number of round trips. And then quantum optics jargon, this parameter here is known as the cooperativity. Another thing you can uses the collection of atoms. In that case, the interaction probability gets scaled with the number of atoms. That parameter is known as the optimal depth. And essentially, you can think of cooperative and optimal depth also in terms of this problem of collection efficiency. So these parameters basically set the kind of branching ratio on information. So imagine I have a single excitation in the atom. And these parameters here describe what's the relative probability that that excitation can emit into this nice Gaussian mode, as opposed to being emitted into other directions of 4 pi that it can't collect. And once you realize that cooperativity and optimal depth are branching ratios of it kind of makes sense that these parameters place fundamental bounds on errors of basically any application that you want to carry out. And the problem is that these numbers cannot be made arbitrarily large. So in the case of a cavity, that makes sense. You can't make a perfectly reflecting mirror. In the case of a collection of atoms, that's not so clear. So why don't I just take all the atoms on the Earth and put that into a quantum memory? The problem there is just kind of technical. So you could try to work with all the atoms on the Earth. Then what happens is simply that this kind of fundamental error you're not going to reach because of all the technical errors associated with trying to use all the atoms on Earth. So just to give you a flavor of what that means in real life. Here's the actual kind of experimental data where you take an atomic ensemble and you try to create a quantum memory for photon qubits. So what's being plotted here is the efficiency of basically 1 minus r as a function of optimal depth and number of atoms. And so what you see is that indeed as you increase the number of atoms, of course the memory gets better. Then you can increase the atoms even more, and then the error actually gets worse again. So that, again, that's this kind of technical error or technical challenge of working with very high optimal depths. So the state of the art, in these experiments, the errors are at 30%. These days, maybe a little bit lower. Likewise, you can look at a photon gate based on atoms. The state of the art experiments still feature an error that's over 50%. So the majority of time, actually, this gate goes wrong. And so, these numbers are maybe kind of humbling because in the end, what we really like is kind of several nines in terms of efficiencies. And so a few years ago, so a lot of people, of course, thinking about ways to get around that. So what's the kind of new way forward? And so now what I'd like to describe is the way that my group has been focused on in the past few years. And to understand the approach, I should actually first point out that what I told you before wasn't exactly correct. So in particular, if you say that the kind of interaction probability gets scaled with the number of atoms, you have some kind of conceptual assumption in mind, which is almost like a photon is like a tennis ball, right? So it has a chance to hit the first atom, if it misses, then it hit the second atom, and so on. And think about a photon as a tennis ball is fine in terms of like quantization of energy. But in terms of propagation, that's not how a photon propagates. So a photon propagates as light or as a wave. And waves interfere. So when you send light into a collection of atoms like this, you have multiple scattering, wave interference, etc. And that can be very strong, even non-perturbative, once the kind of characteristic distance between atoms becomes sub-wavelength. And so, this kind of idea of photon acting as a tennis ball, where it came from in the actual kind of underlying models of quantum optics, is in the story of spontaneous emission. So historically, it's built into our kind of textbook models that when an atom is excited, it's going to emit light into 4 or 5 at a rate gamma naught that's independent of what any other atoms are doing. And so that's where basically kind of wave interference effects get kicked out. And likewise, you can kind of understand that if you have wave interference, so we believe that the total amount of energy emitted out to infinity depends on interferences. Then from the standpoint of the atoms, the correct form of dissipation, the correct dissipation level, has to be some form of correlated dissipation. So it's really that kind of correlated dissipation that my group is really focused on. How can we exploit correlated dissipation? And so let me just kind of, before getting into any details, kind of flash up the main conceptual picture. So on one hand, we want to use light dissipation to create highly efficient atom light interfaces using dense arrays of atoms. So dense array just simply means that you have an array of atoms where the lattice constant, is smaller than the wavelength. And it kind of makes sense when you have ordered arrays, the effects of constructive and destructive interference can be very strong. And so conceptually, you might try to use light in the following way. So now if I create one excitation, that's delocalized within the atoms, I can maybe not only get kind of constructive interference of light into my bit nodes, into my kind of Gaussian mode that I want to collect, but maybe I can use destructive interference to shut off the emission in 4 pi. And of course, destructive interference gets stronger and stronger the more atoms I have. So if I do things properly, maybe I can even shut off the 4 pi emission exponentially with atom numbers. So now when I look at this branching ratio, now I can potentially have something like an exponential in the denominator. And now this branching ratio is going to be way better than this kind of optimal depth answer that appears in textbooks. Another way you can use interference is, maybe you want to just have a photon, kind of hanging around in your atomic ensemble forever. In that case, the photons can kind of mediate interactions and build up correlations, entangling, almost kind of indefinitely. And that might be a kind of new path towards realizing strongly correlated states with atoms and light. So that's the kind of cartoon picture of the program that we started to carry out a few years ago. And now I'd like to go into more details of that. So in the following, I'd like to maybe just give a brief introduction to the theoretical formalism that we use to capture interference in light emission in dense arrays of atoms. And then I'll talk about kind of 2 applications or phenomena. So one is the little few-body physics, trying to use arrays and interference to construct more efficient quantum memories for performing photon-photon gates. And I'd like to talk about kind of many-body phenomena that might appear, which is using kind of long-range light-mediated interactions to generate so-called quantum spin liquids, which are kind of exotic state of matter. Okay, so if you don't work with quantum optics, you might think of kind of atom light interactions as being pretty fundamental, or AMO physics as being fundamental. You can just exactly solve a hydrogen atom, for example. But the point is, in kind of real systems, having a full microscopic quantum theory tractable atom light interactions is probably impossible. And that's just a kind of question of the sheer Hilbert space size. So for example, if I have a collection of atoms, like these 10,000 atoms or more, if each atom is a 2-level system, which is the kind of minimal number of degrees of freedom that I need to talk about interactions with light, then my Hilbert space is now 2 to the 1,000. I also have the atomic positions, which should be kind of shifting around as a function of time. And then I have the photons. So if I'm in free space, I'm propagating photons. So even if I have just one photon, it's going to have any color, direction, polarization. That's a continuum, so it's an infinite dimensional Hilbert space. So that problem is not going to be solved exactly. And so historically, what people did in quantum optics is, you have to kind of treat one of these degrees of freedom as being more important. Historically, people treated the field as being more important. So you try to write down kind of quantum Maxwell's equations, smooth wave equations. The problem is that when you smooth, like then you say my atoms are not really kind of points anymore, but they're just some kind of smooth quantum polarizable medium. When you smooth the atomic positions, you actually get rid of interference because interference and multiple scattering depend on where your scatterers are. And so we want to kind of exploit interference effects. We can't really do that. And so basically, the only choice we have left is to go the other way. So let's kind of, try to throw out the light and treat the atoms as being more important. And so kind of naively, that kind of sounds weird. I'm trying to solve a quantum optics problem by throwing out the light. But let me try to convince you that, that's actually a kind of workable strategy. Okay, so generally the kind of problem that we're interested in is we have a collection of atoms. We shine in light. We assume we know what the is. The light starts to excite atoms. When an atom is excited, it emits a photon. That photon can now kind of multi-scatter and bounce around. And ultimately, that light might come out. And I would like to calculate, any kind of correlation function of the output light. So when I say atom, I'll take a pretty minimal model here. It's a two-level system. The electronic ground state, electronic excited state, with some resonant wavelength lambda g, corresponding frequency omega g. And then if I have just a single isolated atom and it's up in the excited state, then the excited state can drop down to the ground state of the photon with a characteristic rate m and y. So it turns out to be formally easy to integrate out the photons. So certainly classically, we all know that we have this relation that if I have a collection of scatters, I can always write my total field as a coherent sum of what I send in, the input field, plus the scattered field. And it turns out that that equation is correct at the level of quantum operators as well. So the only difference is that in the quantum regime, we have to define a quantum dipole, a quantum radiating dipole. For a two-level atom, that's just going to be given by the atomic coherence, or the coherence between the ground and excited states, or if you want the spin lowering operator. And then I also have this kind of object, this electromagnetic Green's function, which basically kind of propagates the fields from the position of my source, Ri, out to my observation point, R. And this electromagnetic Green's function is nothing more than this kind of, dipole lobe radiation pattern. So this equation is nice because what it really says is, integrating on the field is easy. I know my total fields, provided that I know what all my scatterers or sources are doing. So now I had to figure out what my sources are doing. So you could imagine kind of writing down a Heisenberg equation in motion where a given atom I is driven by the fields. But then I argued on my previous slide that the total field is just kind of a function of all the other atoms. So that allows you to write down a kind of atom-only description of the system, where you basically kind of have photon-mediated interactions. And the form of the interaction makes sense. So you can have a kind of process where an atom J is initially excited, it'll drop down to the ground state, this is by emitting a photon. That photon will then get reabsorbed by the atom I, so you can kind of naturally get a kind of sigma plus, sigma minus, or population exchange interactions. And then kind of intuitively, the amplitude of that interaction depends on how light propagates from atom I, from atom J to atom I. So you get this kind of coherent photon-mediated interactions. You also get kind of correlated dissipation. Here, the specific form of the dissipation doesn't really matter. The only thing that I want to point out is that the dissipation depends on sums over pairs of atoms or basically on atomic correlations. And that's what basically encodes exactly wave interference effects in radiation. So this is essentially our kind of proposed equation one, or re-envisioned equation one for atom light interactions. Okay, so that's the formalism. But then it turns out that for a lot of effects, especially when I'm just sending a single photon, you can understand the physics just from kind of classical optics without, of course, what we do is we explicitly solve the equations, but you can understand all the results just from kind of simple intuition. So let me kind of first tell you about a cute parlor trick that you can play with atoms. So if I take a kind of 2D array of atoms, it turns out that when I shine in weak resonant light, that 2D array can form a perfect mirror for the light. So to understand that, there's basically kind of 4 ingredients. So the first is that when I have isolated atoms, an atom cannot absorb light. So there's no internal degree of freedom to just eat the photon and make the energy disappear. If I shine in a photon, it has to come out somewhere. The second ingredient is that when I have this spatial order, this thing is basically like a drag rating. So it can't scatter into a completely random direction. So for example, I can have a fundamental diffraction order, which is just kind of either transmission or reflection. And then I can have a first diffraction order, where the lattice adds one, let's say 1 unit of reciprocal lattice momentum to make the light scatter in a kind of well-defined angle. The third ingredient is that if I make the lattice constant smaller and smaller, you see that this momentum that the lattice wants to transfer to the light gets bigger and bigger. But eventually that momentum becomes too big, so now the dispersion relation of light is no longer satisfied. So when the lattice constant becomes too small, in particular smaller than the wavelength, all these other diffraction orders shut off or become evanescent, And so the light that I send in, let's say a normal instance, really only transmit or reflects. Okay, so R plus T equals 1. And then the last ingredient is that atoms have a resonance. So to understand that, let me actually just kind of rewrite my initial problem. So I shine the light from one direction. My claim is that on rest is a perfect reflection. What I'd like to do is say that that problem, the solution to that problem, is the sum of the solutions of two different problems. So in particular, it's the coherent sum of a problem where I shine light symmetrically from both directions. So I shine light both from the top and the bottom, and the light has kind of equal phases. Plus I shine in light again from the two directions, but then in one of the directions I put a minus sign on the fields. So let's take this case first. So if I have light that's kind of 180 degrees out of phase, when they meet in the atomic plane, I'm actually going to form a node. So then the atoms don't see the light at all, and vice versa, the light doesn't see the atoms. So in this case, these individual plane waves will just transmit past that plane with no effect. On the other hand, in this case, these two fields form a antinode. And then because the atoms have a resonance, what's going to happen, which is generic to kind of any simple resonator, is that the atoms are going to rescatter the light both the pi phase shifts. So this light is now going to transmit past the atomic plane with the extra phase of -1. And so now I can just kind of add up the results. The total transmission is this kind of downgoing light times -1 plus this downgoing light times +1. So then I conclude that there's no transmitted light. And likewise, I have 100% reflection. Okay, so that's actually been realized in Emmanuel Bloch's group. So they use a kind of, in their case, a quantum gas microscope to prepare basically a defect-free 2D monosilator. They shine fluorescent light, they see a lot of reflection. When you look more carefully, they actually kind of see 60% reflectance. The reason they don't see climb closer to 100% is mainly actually technical. So this experiment was not built as a quantum optics experiment. So it's more just kind of technical issues that prevent them from seeing much higher reflectance. So of course, if you want a mirror, the easiest thing to do is just go buy one at the store. It's very, modern insulator is probably the most expensive mirror you can buy. But the point is, it has quantum functionality. So what you should really kind of view this 100% reflection as is a kind of, is a kind of maybe signature or suggestion that you've achieved 100% atom-like interaction efficiency. And once you do that, you can start to do useful things, since these are atoms. So for example, if you have 100% reflection, that means at some point, during the process, when I shine in a photon, that photon had to have been absorbed by one of the atoms in your array, and then it's subsequently rescattered in the backward direction. So at some point, I'm 100% guaranteed to have created an atomic excitation. Now, if I create that atomic excitation, of course, that thing is just going to instantly emit and create the kind of reflected light. But then I can just use the kind of beauty of atomic physics. I can, while I have this excitation, I can do a kind of shine in an additional kind of classical laser pulse, basically kind of high pulse, to shelve this excitation into a long-lived atomic excitation. And that's basically a quantum memory for photon qubits. I've now taken an incoming photon, stored it into a long-lived atomic excitation. Everything's unitary, so I can just play the whole movie in reverse, spit out the photon at some later time that I want, ideally with 100% efficiency. So that's true for kind of infinite system. For a finite size system, basically there's some kind of errors that you should avoid. So if I have a finite size array, obviously I don't want to shine in a photon whose beam waist is bigger than the edges of my system. If I try to focus light just on the one atom, then of course all the kind of interference effects have disappeared. But there's a kind of pretty robust region somewhere in between where this quantum memory should work pretty well. And if you want to kind of quantify that, you can take an n by n array for kind of typical parameters. And what I'm plotting here on this curve is the optimized error as a function of the linear atom number n. And what's kind of notable is that already for kind of small arrays like 5 by 5, the quantum memory error could be less than 1%.
How is your photon size scaling sensitive?
Sorry, say that again?
So how is your, when you scale system size here, how are you sort of scaling the size of the photon?
Oh, yeah, so that's given by this kind of orange curve here. So what I'm plotting is the ratio of the beam width to the linear dimension. So you see that for big enough systems, it's kind of saturated about like 20.
So it's like a fundamental concept. So some details of the numeric concept.
I think it's actually not constant, so I think it actually like keeps decreasing, but very, very slowly. Yeah. So it is possible to write down kind of analytic expressions, but it's nothing more than the balance of these two effects that I've realized. So a photon memory is passive, but now you can actually try to use the same system to actually build up entanglement. So in particular, imagine I stored the first photon, but I've shelved it into a Rydberg state. So a Rydberg state is a kind of high-lying atomic level. And this kind of Rydberg state, what it does is it has a kind of exerts a very strong influence on all the atoms in its vicinity. So this dispersive interaction can actually shift the resonance frequency of all the atoms within some, let's say so-called blockade radius. And so what it does is that, for these atoms here, it can still be perfectly reflecting, but a completely different frequency of input level. So now if I shine a second photon at the bare frequency of the atoms, from the standpoint of that second photon, this Rydberg excitation basically punches a big hole into my mirror. So now I've achieved a situation where, depending on the absence or presence of the first photon, I can condition my kind of mirror to be reflecting or transmitting for the second photon. So you can use that to build up entanglement or basically a photon A. Again, for kind of realistic parameters, you can blockade a few lattice sites. That error becomes on the 1% level. Okay, so now I'd like to switch gears a bit. So up to now, I've discussed how you can use strong wave interference effects to, in principle, build very efficient quantum memories gates. So these are kind of single photon level applications. And now what I'd like to discuss is how to start using these ingredients to generate more kind of complex, many-body, strongly correlated phenomena. So this is a topic we're interested in the group, in general. And here, what I like to do is just give one example of a phenomenon that we're studying, which is to try and induce so-called topological quantum spin liquids. So probably most people's introductions to topological quantum spin liquids, or certainly the easiest introduction, is the so-called Kitaya toric code. It's an exactly solvable model. Unfortunately, though, the Hamiltonian is just a little bit kind of disconnected from the kind of physical systems that we have in mind. So I'd like to kind of take a little bit more kind of circuitous roundabout route to introduce spin liquids here, particularly in the context of frustrated antiferromagnetic Heisenberg models. And a kind of famous one that appears in the literature is the so-called J1, J2 model on a square lattice. So basically, I have an interaction strength, J1, an antiferromagnetic interaction that acts on kind of like the nearest neighbors along the vertical horizontal links. That wants to create mail order in those kind of horizontal and vertical directions. But I have a competing or frustrating interaction. So I have a separate J2 that instead wants to create antiferromagnetic order along the diagonals. And then the question is, what's the kind of ground state of that system? Is it possible that the ground state somehow avoids, avoids antiferromagnetic order entirely? So questions like this of, what's the ground state of a kind of, antiferromagnetic Heisenberg model? That's a question that's quite old, dates back, 30, 40 years or more. And so what I'd like to do is now is kind of describe a theoretical technique that was developed in the late 80s and early 90s to, try and answer this question. And really, the next couple of slides are going to look a little bit kind of mathematically abstract and random, but I promise that there's a kind of interesting punchline at the end. So please just kind of bear with. Okay, so what people, kind of mathematically minded physicists did as well is that I like half integrals, so I'm going to try throwing half integrals at the problem. And the first thing that is pretty well known is that when you're putting out spins, that doesn't kind of fit very well with half integral methods. It's much easier to work with bosons or fermions. So people just said, well, now I'm going to again, do math and turn spins into fermions. What that means is, you can say I have a given spin, I, and then in the fermion language, I can say that, that site I actually has either has no fermions, spin down fermion or spin up fermion or two fermions. And of course, now my Hilbert space is expanded. My physical Hilbert space is to have exactly one spin per site. So the mapping from spins to fermions is just formally, a spin operator that turns into a quadratic product of fermions. What that just means in practice is that when you have this, if you take this original Heisenberg interaction, now you turn it into an interacting accorded fermionic theory. And again, you have this strain on the physical space. And whenever you do that, almost by definition, you have a gauge theory. What that means is that, again, my physical space is that, I have to have exactly one fermion on a site. Or likewise, if I try to annihilate two fermions and create two fermions, that has to turn into the vacuum or zero. And so what you can do mathematically is to say, I'm going to take these operators on the left-hand side and call them generators. So on the physical space, these generators are zero. And so then if I take e to the I v dot g, you see that on the physical space, these transformations have no physical effects. Okay, so you can think of these, e to the I v dot g as kind of local gauge transformations that keep the physical content of your theory unchanged, okay, but basically just add some kind of redundancy to your system. Okay, so of course, it's very hard to solve quartic fermionic Hamiltonians in general. So then people start playing tricks, even more tricks. So then you can say, well, instead of having a direct interaction between fermions on sites I and j, I can introduce a new bosonic fields with which the fermions on I and j directly interact, and that bosonic field then mediates interactions between the fermions on I and j. And so by doing that, you reduce the order of the interaction to being quadratic in fermions times linear in this mediating bosonic fields. And essentially, because I started with the gauge theory, because I started with this redundancy, that gets transferred over to this new theory as well. And then formally, you can interpret this kind of new bosonic field as a gauge boson, or like an effective photon, if you want. Okay, so that's still too complicated to solve. So let's do even more. Let's just make the kind of wild assumption that we can replace this bosonic quantum field with just a number. So kind of like mean field theory. And when you do that, finally you get a kind of simple Hamiltonian. It's just purely quadratic in fermions. So it's easy to solve. You can construct spin correlations, etc. Okay, and now you should say, well, what the heck was all that for? Is that just kind of all mathematical nonsense or trickery? So I've taken an original seemingly harmless spin model, I've decorated it into the language of lattice gauge theories and fermions. And so, what does it mean? Is it all mathematical trickery? Well, one kind of particular component is that if I look at the original Heisenberg model, the total angular momentum S and the projection SE are good quantum numbers. What that means is that if I have an even number of spins, then my fundamental excitations in the system should carry integer S and SC. But now when I look at this mean field Hamiltonian at the level of fermions, if I were to interpret that literally, this Hamiltonian says that my fundamental excitations in my system carry half integer spin, right, because they're fermions. And not only that, these kind of spin-on excitations have fermionic statistics. So how do I reconcile this statement here with this thing here? Well, it had to be that some kind of assumption I made along the way was too drastic. And in particular, is this kind of mean fields assumption. So anytime I have a kind of gauge boson, like a massless gauge boson or a photon, that photon can propagate long distances. It can mediate long-range interactions between the fermions. And generically, what's going to happen is that it's going to glue those fermions back together. Okay, so this kind of free fermion picture here is too naive because of strong beyond mean fields effects. So at that level, you would say, yeah, probably what I introduced up to now is just all mathematical trickery. But then, Shao Wen is really just kind of beautiful work, so maybe not so fast. So we know that in nature, there can exist mechanisms where massless bosonic field can become massive. So a Higgs mechanism, if you want. And so, if that happens, then actually something beautiful occurs. So now these kind of gauge fields, these massive gauge fields, they can no longer mediate long-range interactions between the fermions. These fermions get far enough apart, they essentially actually become free or real particles. So I now have genuine fermionic excitations from a fundamentally from a fundamental spin system. So I have the emergence of fractional spin statistics. And likewise, this kind of lattice, this gauge boson that I introduced before, also develops a real kind of life on its own. So, now I conclude that this kind of spin system, I can get the physics of, emergent physics of fermions, gauge fields. It's almost like kind of standard model type physics. So to me, it's one of the most beautiful examples of emergent physics that one can imagine. So that's basically an introduction to quantum spin liquids and their fundamental excitations. So up until now, my introduction of quantum spin liquids is a little bit abstract. Now let's actually just study what the kind of physical wave function looks like. So of course you can't solve a generic Hamiltonian exactly, but what you can do is, if you believe in this kind of mean field approach, you can try to just project out all the kind of unphysical states, where you have either 0 fermions or 2 fermions per side to get at least a kind of legal spin wave function. And what you tend to get is a picture like the following. So what I'm showing here, so in a given kind of, what this picture shows, is that I take any spin, I pair it up with some close by other spin into a singlet pair. So basically, I just kind of cover my lattice with a bunch of short range singlets. Now, if I only did that once, obviously just because of the way I kind of chose the singlets, that state breaks, translational symmetry, rotational symmetry, etc. But then, in this kind of approximation, what you find is that the true ground state of these spin liquids is like a massive superposition of all of those things. And it's that massive superposition that basically restores translational symmetry, rotational symmetry, etc. And what you see is that this kind of spin liquid ground state basically has no kind of obvious ordering to it. So the main message here is that basically these kind of spin liquid ground states are just kind of massive superpositions of singlet states. Okay, so that's just the physics of spin liquids in general. And now what I'd like to do is discuss whether it's possible to create quantum spin liquids using atoms of light. So again, here's the kind of Hamiltonian or master equation that I showed before, where I integrate out the photons to get an effective spin description. And what we were generally interested in is kind of coaxing out interesting many-body phenomena from this model. And so again, the kind of 3 main ingredients are that somehow we'd like to exploit correlated dissipation. So we'd like to encode a spin liquid ground state in a manifold that doesn't radiate light. Somehow we have to kind of get the spin liquid or any other phenomena that we're interested in from long-range interactions, because naturally photons propagate everywhere. You want to induce long-range interactions between the atoms. And then maybe just something to keep in mind is that there's, I don't know, maybe you could call it urban myth that when you have long-range interactions, that tends to facilitate either mean field phenomena or collective spin physics. Obviously, a spin liquid is not collective spin and mean field. So somehow we want to avoid mean field type behavior. All right, so let me introduce a minimal model where we think we can get spin liquids up. So that's just going to be a collection of 2-level spins, 2-level atoms, coupled to a single cavity mode, a so-called James-Cummings or Titus-Cummings model. So in this case, the interaction is that I can annihilate a cavity photon and excite any one of the atoms in a symmetric fashion. So the atoms couple symmetrically to this one bosonic code. So in the case where my kind of atomic resonance frequency, my cavity resonance frequencies are different, I can integrate out the photons, just like I described before. And then what I get is a kind of completely symmetric or all-to-all sigma plus, sigma minus interaction. And again, that's just specifically because the cavity couples to all the atoms in an equal fashion. And because of this kind of high permutational symmetry, I can rewrite that coherent Hamiltonian just in terms of collective spin operators. So that turns out to be, s squared minus sc squared. If I have cavity dissipation, so if the photon that's circulating around, eventually kind of dissipates out, that's going to induce some effective dissipation on my atoms. And that's going to be described by a kind of jump operator, which is just simply a collective spin lowering operator. So when I lose a photon, what that's going to do from the standpoint of the atoms is it's going to lower the atomic spin, but in a completely symmetric way. So one thing I should mention here is that up to now, when I talked about kind of protecting atomic states from dissipation, I was really talking about all forms of spontaneity. So not just kind of emission into the cavity, but also into 4 pi. And what I'm going to talk about going forward, we're going to neglect the 4 pi emission. Or another way of saying that is the spin liquids that I'm talking about here are not truly protected from this 4 pi emission in the same sense that I was saying before. The only reason for that is, we tried, but it's just kind of, we bit off more than we could chew. And so we don't know how to deal with this kind of 4 pi emission yet. Okay, and then, basically because this whole thing is kind of collective spins, then you can kind of see where this kind of picture of collective spin comes from. So typically people work in a sector where the spin is macroscopic, so that gives rise to the spin squeezing, cheeky super radiance, etc. But to reach complexity, what I can do is something simple. I can choose the kind of coefficient in front of this interaction to be positive. In that case, the ground state is going to occur, the zero energy ground state is going to occur when both S and SC are 0. So the physical picture of the energy diagram is this. I have this S equals 0 manifold. So I have a total spin of 0. That's going to be the ground state manifold of this cavity Hamiltonian. And then if I have S equals 1, that's going to be gapped by a large energy difference T. And then I have S equals 2, and so on. And so then you can ask, what is the basis of S equals 0? What kind of states are contained in S equals 0? Well, to create a total angular momentum 0 state, I just basically have to guarantee that every atom is paired up with another atom to form a singlet state. So this S equals 0 manifold contains exactly these kind of quantum spin liquid states that I illustrated before. It also contains these so-called valence bond solids. It also contains just kind of completely arbitrary pairings because the cavity doesn't know anything really about geometry or space. Okay, so the point is, there is something interesting in the sector, full of other things that we don't necessarily want either. So what do we do with that? But I'm sorry, I should also say that in the S equals 0 sector, so this quantum spin liquid state, because the spin is 0, it's also dark to the cavity emission. So if I just gave you the quantum spin liquid to begin with, you would never see a photon come out of the cavity. So it's protected from dissipation, at least in that sense. So to pull out this kind of quantum spin liquid state, we can take some inspiration from Michelangelo. There's this kind of urban myth that he said that he never sculpted David. So that David was already in the marble, and all he had to do was chip away at everything that wasn't David. So let's try to chip away at everything that's not quantum spin liquid. The way we can do that in the regime is to just add a perturbation to the Hamiltonian. And hopefully if we can add a perturbation in the correct way, we're going to split up this highly degenerate S equals 0 manifold. And if we're lucky, maybe the true ground state will be exactly the quantum spin liquid that we're looking for. Okay, so what's the perturbation? It's just going to be kind of something that we think is physically realistic. So it's going to be some short range Rydberg or Ron IC interaction. So to the original kind of all-to-all cavity interactions, we're going to add a short range antiferromagnetic IC interaction. And to treat this term as a perturbation, we're going to assume that the cavity is much stronger than this J. So let's think about what happens. So if I only have the cavity, again, I have this kind of extensively degenerate S equals 0 sector, which is the big gap to S equals 1 and higher sectors. Now, if I add a small perturbation, I can basically do a kind of so-called Freeper-Wolf transformation. So it's the lowest order in perturbation theory or many-body perturbation theory. You want my new effective Hamiltonian for this S equals 0 sector is given by the projection of this perturbation into the S equals 0 sector itself. So this is my new effective Hamiltonian which describes the eigenvalues and eigenstates here. Now, generically, if I project into kind of correlated sectors, that's a very hard thing to treat. But here there's a kind of magic trick. So if I have a global singlet state, that state is invariant under global spin rotations. Now, the Ising model is obviously not, right, because I prefer the direction Z. So if I project the Ising interaction, Ising-Hamiltonian, into a rotation invariant version of itself, I basically get out a short-range Heisenberg model. So the statement is that the low energy physics of the system with this kind of weak Ising perturbation is described by a short-range Heisenberg model, where my J's are simply taken from directly from this kind of short-range Ising model. So it's kind of interesting effect because it does have these kind of global all-to-all interactions. But what I'm saying is that when these all-to-all interactions are very strong, essentially my low energy physics sector, I get an effective short-range model instead. What I do want to emphasize though is that that kind of mapping to a Heisenberg model is really only kind of true in the x=0 sector. That's where I can play this trick of rotational variance. In the higher sectors, I really do have to deal with this complication of the projectors. Okay, so now we've kind of arrived at the main punchline. If I want to create a quantum spin liquid using a cavity, I just have to find a corresponding Heisenberg model that supports a quantum spin liquid. And one that's proposed, I believe, to hold a spin liquid is this J1, J2 model on a square lattice that I presented earlier. So the details of the phase diagram of this model are a little bit kind of still under debate, but I think most people kind of generally agree on the broad features. So as a ratio of J2 to J1, either for very large J1 or very large J2, then I form a kind of male antiferromagnetic state, so it's magnetically ordered. But there's some intermediate value in between. It's believed that there's some type of quantum spin liquid phase and maybe kind of a valence bond solid phase as well. So now if I want to realize that J1, J2 Heisenberg model, again, the trick is the following. So I put all my atoms into a cavity. I turn on very strongly the all-to-all interactions. And I add in a weak J1, J2 Ising, or basically classical Ising interaction at the same time. And then the idea is that these kind of cavity fluctuations will melt the kind of classical order that I get from this classical Ising model into a quantum spin liquid. So just in pictures, here's the kind of same ratio of J2 over J1. If you believe everything I've set up to now, if I crank up the cavity interaction strong enough, then my phase diagram should look exactly like a corresponding Heisenberg model. So I should get the same antiferromagnetic phases, the same valence bond solid phase, and this quantum spin liquid phase that I'm really interested in. Then you can also ask, well, what's the kind of rest of the phase diagram? So what other phases are there in the system? So I'll make the following two claims, and then I'll try to support that with some simple arguments. So first of all, if I have no cavity interaction, basically this line here, then the Hamiltonian is pretty simple, just a classical IC model. So I get kind of classical nail order. And then my first claim is that now if I turn up the cavity interaction, I'll basically get a kind of squeezed version of my classical state. The second statement, which is maybe a little more non-trivial, is that actually to have a kind of phase transition, I'll need to rescale my cavity-mediated interaction so that it grows extensively with the atom number. And one way to kind of understand that intuitively is that I want the cavity to have a kind of projective effect, so the strength of the cavity has to grow extensively. So of course, in real life, I can't just put more and more atoms into my cavity and just magically turn up the cavity interaction. It doesn't work that way. So another way of saying this, if you want, is that this kind of phase up here, so this effective Heisenberg model phases, that's essentially a finite size effect. So it's not a true phase in the thermodynamic limit, but in a real system where I have hundreds of thousands of atoms, that's not an issue. Okay, so let me just try to substantiate those claims in a little bit more detail. And to do that, you don't need to study something like cyclotic spin liquids. You can just study the same model in 1D. So I'll consider all-to-all interactions in 1D plus the nearest neighbor Ising interaction. So again, when the cavity is completely turned off, then I just get this kind of classical mail ordering, where let's say, I divide my lattice into sub-lattices A and B. All the spins on sub-lattice A are pointing down, all on B are pointing up. In terms of a picture, I can think of these as two giant collective spins. So I can think of all of the spins on A as a giant kind of collective upspin, and likewise all of the spins on B as a giant collective downspin. And because this is a kind of product state, these spins are uncorrelated. They each have some kind of transverse noise, or noise in the kind of SX and SY directions. And so now, when I turn on the cavity interaction knows about the transverse components, and the cavity is basically going to give a kind of energy penalty to this kind of transverse spin noise. So it's going to give an energy penalty on the order of n. But one simple way to kind of reduce that energy penalty is to introduce EPR type of correlations. So EPR in the kind of language of harmonic oscillators means that the difference between, let's say, two modes XA and XB, the positions goes to 0, and the sum of their momentum also goes to 0. And that's not permitted by quantum mechanics because these two operators compete with each other. So in the spin language, what that simply means is that these kind of transverse noise fluctuations become correlated. So if A happens to fluctuate to the left, then B will happen to fluctuate to the right. So the total spin noise in the transverse direction gets shrunk down to a small value. So that basically describes the kind of phase diagram when the cavity is weak. What happens is if we're on a kind of finite spin system, if I try to squeeze too strongly, so if I try to correlate the transverse directions too much, then actually I'll reduce my spin component along Z. So that'll give an energy penalty in turn to the IC interaction. So at some point, that interaction, that squeezing becomes unfavorable. Then I enter into this Heisenberg phase. And then, by kind of just simply creating some variational ansatz for these two systems, I can estimate that my phase transition between these two modes goes like T prime over J is something like 10 to the minus 2. But again, the important thing is that this T prime already has this kind of extensive, n scaling factor out. Then, we can do more kind of complete numerical simulations like DMRT to really verify that behavior. So we feel like we understand these phases and phase transition pretty well. Okay, so with that, I'm basically done. Maybe just a kind of quick outlook. I think we've found kind of interesting paradigms to realize quantum spin liquids using long-range atom-light interactions. At the same time, though, I think there's kind of many interesting questions and opportunities left to think about. So you could ask, why use cavities in the first place? So there's certainly real candidates for spin liquids that exist in real life. And so that's kind of some of the sets of questions that we're interested in. So can the cavity provide kind of interesting measurement tools, maybe to measure the dynamic structure factor, which gives you a kind of signature of quantum spin liquid behavior. I think it's also nice to go back and think about this dissipative aspect of the problem in more detail. So as I said before, the cavity-mediated spontaneous emission is described by a collective lowering operator of the space. And so if I gave you any state in the S equals 0 radical, so if I gave you this quantum spin liquid state to begin with, for one thing, you would never see a photon come out of it. So if you did see a photon coming out of the cavity, and then you presumably created a pair of these kind of fractional spin-on excitations along the way. So one of the questions we're interested in is, if we could somehow measure photon correlations, is there anything hidden in there, let's say about which contains information that you have these kind of effective fractional excitations or anyons flying around your system? At the same time, since the target state is kind of dark, we could ask if that leads to more robust methods of state preparation. You could also ask, well, again, in what I set up now, this state, if I created it, it's not robust to free space with 4 pi emission. So we're interested in, seeing whether we can code the state to be robust also to the 4 pi light emission. Obviously, this whole system is kind of out of equilibrium because of dissipation, so on. We're generally interested in how to treat, even how to think about non-equilibrium dynamics, for something as complex as spin liquids and topological order states. one thing that you saw is that, when I put on this kind of strong cavity field, my effective low range Hamiltonian is actually a short range isotope problem. So one thing we're interested in is about, light information propagation in systems, so some form of Lee Robinson balance fold, at least maybe in a limited setting. And then again, just to go more back to the original picture, beyond spin liquids per se, I'm really kind of excited about maybe opening up a new future of atoms and light, really coming from this combination of long range coherent interactions and protection by collective dissipation. So with that, thanks for your time, and I'm happy to answer any questions. Thank you.
For this like square J1 J2 model, the recurring interaction would give you like a fixed big two digit one that isn't from that 0.45 per given quantity. So how do you get around that?
Oh, right. Yeah, so I didn't say how we imagine implementing it. So I think realistically, like if it's an optical transition, so actually in real life, your happy QD interaction is going to be much weaker than your bare Rydberg interaction. So to be able to explore this kind of regime where the effective is weak, you probably have to go to a Rydberg dressing regime, and then in principle you have the flexibility to.
But I guess if you like make it weak enough such that your J2 can actually get like half of your J1, then your J3 is also half of your J2. So your model is going to be not interpreted.
Yeah, so right, so this J1, J2 is some kind of point model, right? You could ask, right, if I have tails beyond that, does this space still persist? That's not something we studied extensively. My feeling is, there's some way, there should be some regime where the phase persists, because phases usually aren't kind of like singular parts. But yeah, it's not something we've explicitly looked at yet. Probably also because just the numerics is very challenging.
Yeah. For the photonic gate part of how the gate fidelity scales if your atomic position is not that accurate, for example, like this off by 100% of the wavelength, and also the atomic wave functions distribution.
Yeah, so maybe the more relevant question. So I guess we presume that the way you create these subwavelength arrays is that the atoms will be followed by multiple lattice. So we don't really consider like classical position disorder. But yeah, even if you don't have this kind of classical disorder, you still have this quantum, even like quantum 0 point motion. So then in that case, you do get this kind of additional error that basically scales with the so-called lambda e parameter squared. So as long as your atoms are tight, perhaps then that error should be only a percent.
So for this second half of the story, where you said you're not including the 4 pi emission because the thin liquid, I guess, doesn't intrinsically suppress that. What cooperativity would one need for the single atom such as 4 pi emission?
Yeah, so we don't have a very precise answer to that question at the moment. I guess it's very much tied to this question of how do you prepare the state in the first place, and whether you could take advantage of, let's say, this collective dissipation to maybe do faster than adiabatic evolution. So if I had to guess, probably on the order of 100, but again, that's just a kind of guess. It's not substantiated in any real.
I mean, the good news is in circuit QED they have 100 billion. So,
Right.
I mean, I guess I'm just wondering, we are talking about 100, and not that it's going to need to be 10 to the 50.
I don't see why not. So I guess the worst case is like even if you don't prepare the ground state, you prepare a low energy state. Okay, then you'll have some of these kind of spin-ons flying around. But I don't see the issue with that. Right, the goal I think is really to show that you have these spin-ons, they have fraction splits, and so on. So you don't need a ground state per se.
Maybe actually related to that, maybe you said it and I missed it. Assuming you do need to do the adiabatic preparation, how does the relevant that scale?
So that
Maybe
we
briefly. Yeah,
yeah, so we haven't really looked at that either. Essentially, the problem, which is also tied to John's question, is it's a little bit like a chicken egg problem. So like to answer how much cooperativity and stuff you need, I think you need to be able to answer several questions at the same time, which are kind of all challenging. So one is just right. If you in fact compare, you don't get to the ground state, you get some non-equilibrium state. Then the question is, now that you have this non-equilibrium state, how do you think about? So for example, if I have a spin liquid and I say it's a temperature, then I feel like you have the kind of mathematical technology to say here's the properties that you see. But then when it's non-equilibrium, it's a little bit challenging to say in what sense is it a spin liquid? What can I measure to say for sure it's a spin
yeah, I
liquid?
think it's asking
So-
some more basic question, like, is there some gap that sets a characteristic scale? Getting this data, and then there's a question for how slow you have to be.
Yeah, so for sure there
Yeah.
is, but we haven't looked at a particular kind of way to automatically move into the spin liquid state. So in that sense, I can't give you a concrete answer.
So it seemed like, you're generating all these local interactions, river interactions, they have to be arranged in this J1, J2 pattern. The thing that the cavity field is doing here is just changing that from an Ising type interaction to an Heisenberg type interaction, and that's the whole role of the cavity?
In the current setting, yeah. So right, we use the Rydberg to create this classical Ising model, and then the quantum fluctuations in the cavity give the state all its quantum character in the end. One thing we are interested in is whether. So what it describes is basically a concrete prescription of one way to get a spin liquid. We're also exploring other ways that really use the cavity, this kind of projective nature of the cavity to get a spin liquid that doesn't necessarily involve kind of starting from a Ising model and then turning into a Heisenberg model.
This analysis that you do for like this mapping to gauge bosons with the spin liquid, are the gauge bosons dynamical or it's a static gauge field?
No, in principle, it's a dynamical. It's a legitimate kind of low energy degree of freedom.
Okay. And then is this same sort of that analysis is for like equilibrium stat map? Is that right? Or is it?
So the mapping, I guess, is true in general. So you could have, right, first of all, you could say that, I take this as some positive equilibrium, now say in Hamiltonian, the effect of Lattice gauge theory also holds for the non-equilibrium dynamics. But historically, the way that people use this was to analyze equilibrium properties.
I just mean like the phase diagram that you showed was for.
So the phase diagram I showed was purely a ground state phase diagram, right? So it doesn't capture this kind of the fact that our system is really non-equilibrium in the end.
Thank you.
Okay, Sarah, one more question for Dave.
I was just curious, like how robust these things are to like the phasing and the disorder.
So in principle, so it's a topological order phase, which means in principle you could add. So if you have static terms to the whole thing, you don't need any particular symmetries to realize these kind of topological order phases. So I'd say that, I mean, for a particular perturbation, you would have to see at what strength you can add it before you enter a new phase. But in principle, these are phases that are robust to arbitrary perturbations. If you have dephasing, which is kind of more like dynamical and consistent, then it's I think a question of how long topological order, so you have some signature of topological order that you're looking for. How long does that survive, or how does topological order apply? That's definitely a question we're interested in, because again, our whole system is not a group, so we can't avoid those questions anyway. But at least at the moment, we find that to be a kind of very tough question to crack.
Okay, let's thank Darrick one more time.
Yeah.